Transition metals, or as we call them, D block elements, they are basically in the D block in the periodic table. You know, there are blocks in the periodic table that we have. So periodic table is roughly like this. These are blocks called S, P, D, and F. These two are also in S, but unko placement hum thodi si idhar udhar kar dete hain unki, because hydrogen acts like both group 1 and non-metals, and helium acts more like noble gases and less like group 2. So इस वजह से हम उसको यहाँ पे रख देते हैं. But other than that, this is how the general arrangement of the periodic table is. Sorry, this should be D and this should be P. And in AS, we talked about how electrons are arranged based on this. So for example, if something is in fifth column in P block, then its last electrons will be in P5. Similarly, if something is in second column of S block, so uski configuration hoti hai S2, whatever the shell number is. Similarly, if something is in the seventh column in D, तो उसकी configuration होती है D7. That basically shows how the electrons are arranged. So if you think about it, in the periodic table, we are going to restrict ourselves to just the fourth period for the transition metals today. So that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Yeah, that's how these are. And if I look at their arrangement, all of these have 4s2 and argon. That's where they start. Scandium has 21 protons. So it starts after calcium. So calcium ki configuration is already included in there. So calcium's configuration is argon's configuration and then 4s2. Another way to look at how it will be 4s2 is कि बिल्कुल D block के शुरू होने से पहले you have fourth row and second column of S block. So 4s2. Uske baad you will start. Now D block is always one step behind the regular period that you have. So the configuration of scandium is 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. That is what rudimentary analysis might give us. But then if you look at the shells or the way orbitals are arranged, then D has 5 orbitals. In these 5 orbitals, here are how the electrons are going to be started. So I'm starting with scandium. So scandium has 1. By the way, they all already have 4s2. Okay. I should, because it has high energy, I'll just put it here. So a filled 4s2 has higher energy than 3d. Okay, so I have 2 electrons here. So as I add electrons, this is scandium right now, titanium, vanadium, chromium, and this should work. But then if you look over here, chromium is just 1/2 orbital away from having a very stable configuration. अगर इसको किसी तरह यहाँ पे एक इलेक्ट्रॉन मिल जाए तो ये half filled हो जाएगा, and half filled subshells have a special kind of stability, and that is what happens here. The 4s loses an electron and the electron is brought down to 3d. Now we can show this electron as this, and there is nothing wrong with the way electron is arranged right now, but just for the sake of convention हम इसको ऐसे कर देंगे. This is basically showing कि उसका spin जो है वो ऐसे है. Although जरूरी नहीं है कि इसका spin और इसका spin एक जैसा हो, जरूरी नहीं है. But it's just कि इस orbital के अंदर कोई दूसरी चीज same spin के साथ नहीं आ सकती. तो that's fine. अगर वो उल्टा भी होता, that was also correct. But that is why chromium, instead of staying at 3d4, chromium has a special kind of arrangement where it is 3d5, 4s1, not 4s2, 3d5, 4s1. Now let's keep on adding electron. Let's bring this one back to 4s2, and now you have एक और electron add हो गया, manganese. Then we have another one, iron. Then we have cobalt, nickel, copper, and again, same idea. Copper is one electron away from having a complete shell. And that is what it does. That is what it tries to do, that it brings this one over here, ताकि उसका shell complete हो जाए. So it brings it here, and we get 3d10 instead of 3d9. So it becomes 3d10 with 4s1. So these are two special cases of configuration in the case of chromium and that. And then we have zinc, which is, there you go. Okay, so that's how the arrangement is. Now, how about the ions? When we remove electrons from those, how do those electrons come out to be? So if you look over here, let's start with, I don't know, let's start with zinc. So zinc has 2 electrons in the last shell. And by the way, because the last shell over here is 4s2, it has the highest energy. So the last electrons that it's going to remove are going to be from 4s, not from D anymore. It is 4s that will remove those electrons. Okay. So that is what happens here. So it loses these, and we are able to get what you call the 2 electrons are lost, and we get this thing. And the configuration of ion, now let me draw the ion. Zinc has formed +2, and that is good enough. Zinc has a stable subshell. It does not need to kind of like gain any more stability. So zinc ko zarurat hi koi nahi hai. And that is what zinc does. Zinc will keep it like that. It does not need to lose any more electrons. Clear? So zinc forms +2 only. How about, let's go back to copper. Copper has this configuration. And when this is going to lose electrons, the easiest way to lose electron is to lose this one. It does that. So we are going to get copper +1, which has 3d10 configuration. Zinc also had 3d10 configuration. But copper, remember, it had an electron that it has already lost. So it had already brought down from 4s. So when it comes to losing it, that is the first one to go. So वो उसको lose कर सकता है. And that is why we are able to get copper +2 as well, which is 3d9. By the way, when it comes to metallic bonding, these electrons lose their valence electrons to the metallic bonding. And in all of their cases, except for copper, it is 2 electrons. Copper जो है वो थोड़े से extra electrons दे सकता है. And that is why copper has some extra, what you call, conductivity. It's a really good conductor compared to the rest of them. Okay, how about nickel? So again, nickel is like 3d8. So it has lost this electron. And yeah, so sorry, this should be in the opposite spin. Okay, so nickel can lose the 2 electrons in 4s. So ये इन दोनों को lose कर सकता है, giving us nickel +2. And then there is no special stability that nickel might gain by losing anymore. इन दोनों को lose कर सकता है, sure, but then it can also lose 1, 2, and 3. So we might expect nickel +5 to be made. But there's a challenge there. Nickel has a very small radius, a very high effective nuclear charge. So it is very protective of these electrons that it has in the 3D. So nickel stays with +2. The high effective nuclear charge makes it difficult for nickel to lose any more electrons with reasonable energy. काफी ज़्यादा energy लग जाती है, so it doesn't usually do that. We can force it to, but it doesn't usually do that. In the case of cobalt, cobalt is 3d7, which is this one. So cobalt does that. कि cobalt configuration होती है +2, तो वो इनको lose करके बन जाएगा. But then, due to certain reasons, cobalt can sometimes make +3 as well. Okay, so cobalt can also make cobalt +3. If you look at the configuration in this case, nickel is the configuration of nickel would be 3d8 थी, तो वो 3d8 ही रहेगा because उसने 4s2 remove कर दिया. Cobalt की configuration 3d7 होगी या 3d6 होगी. That's what it's going to have. In the case of iron, everybody knows iron has this situation. So iron can lose the 2 electrons here. So वो तो बड़े आराम से iron plus 2 बनाता है. But then iron can also lose this one extra one. So if it loses that one as well, so you get iron plus 3, which is also a reasonable stability that it can achieve. So 3d5. Okay, so 3d5 and 3d6. Sorry, 3d6. Let's continue. Manganese. Manganese is very versatile. It has not very high effective nuclear charge. Iron ke baad, it becomes really a pain for the iron to lose any more electrons because of strong effective nuclear charge, minimal shielding. But manganese ke case mein, there's a very strong balance there. So uski wajah se kya hota hai ki manganese, which is like this right now, manganese in dono ko remove kar sakta hai. It does that. So manganese plus 2 is there. Colorless hota hai usually with oxides. Manganese can also remove 2 of them. And that's like, ye kya hua hai? Like, why is suddenly manganese losing 2 electrons from 3D? Usse kaun si aisi koi usse special stability mil rahi hai? We will get to that in a bit. Ki aisa kya special hai in removing 2 electrons here. And then manganese can also remove 2 more. Okay. And that will give the manganese plus 6. That's also there. And then manganese can also remove the 3D ka aakhri wala, and that is manganese plus 7. Many questions hai. Ye kya ho raha hai? Hame samajh aa rahi hai ki wo 4s2 kyun kar raha hai. It can remove that, have a 3D half-filled subshell. But 3D mein se phir further remove karna? Weird. Do or remove karna? Even weird. Plus 7 samajh aata hai, it wants an empty 3D. That makes sense. So we will come to that. Why is manganese such a strong chameleon? Kaise wo kar raha hai? What's happening at the atomic level? Okay. And yep, 4s1 and 3d5, that is chromium. Now chromium can lose the 4s2 wala, and it can also lose the one that it gave away. That is possible, plus 2 ho jata hai. But then chromium can also lose 2 more, making it chromium 3, which is the one that we will also deal with. Hamare syllabus mein chromium 3 plus zyada important hai. Similarly, chromium can also lose others, and that will be chromium plus 6. Vanadium ke case mein, there's a whole versatile range. So vanadium can lose the last 2 from 4s, good enough. Vanadium, which is like this basically, vanadium 3d3 hota hai na? So yeah. So vanadium can remove the last 2 from 4s2, that's fine. It can also remove 1 more from 3d. It can also remove 1 more from 3d, and it can also remove another one, making the 3d completely empty. So V plus 2 plus 3 plus 4 plus 5, sab ke sab hote hain. Okay. And again, you can clearly see that as you're moving towards the left side, effective nuclear charge itna strong nahi hai. Iron ke baad effective nuclear charge is very, very strong. And that is how it is. In the case of titanium, arrangement is pretty straightforward. Last 2 ko remove karta hai. Apna ek already yahan se bhi remove kar deta hai. And it can also remove both of these. So titanium plus 2 bhi hota hai, plus 3 bhi hota hai, plus 4 bhi hota hai. And in the case of scandium, this is what you have, 4s2, 3d1. So scandium loses all 3 of them. It doesn't keep any one of them. Sare remove karta hai, and you get plus 3 scandium. Okay, let's look at the arrangement of these. So this is 3d0. And the rest of them have some variation in 3d. There are 2 of them, scandium and zinc, जिनका 3D या तो complete है या है ही नहीं, खत्म हो गया. And this is where we are going to define what a transition metal is. Transition metal forms iron with incomplete d orbital. Incomplete d orbital is important, and that's not happening here. In the case of zinc, you have a complete d orbital, not a transition metal. In the case of scandium, you have 3d0, 3d khatam ho gaya, not a transition metal. Okay, so
Sir?
Yeah.
Sir, Mn plus 7 के साथ भी 3D like खत्म ही हो जाता.
हो जाता है. You're absolutely right. Not just this,
So-
vanadium 5 के साथ भी खत्म हो जाता है. But can it still make this or this or this? there is at least one ion that it has made which has an incomplete d orbital. So here's
That's
the
it.
yeah, so that's one key idea. Second one, when they're trying to make electrons or trying to lose electrons, you can see that all of them are making +2. And that is because 4s2 electrons are removed first because they have the higher energy after they're filled up. And the maximum oxidation number, the maximum valency that they have, oxidation number, is when 4s and 3d is emptied. So for example, in vanadium, you have +5, क्योंकि उसमें D में 3 थे, 4s में 2 थे, total +5 वो remove कर सकता है. Manganese has 7 because 2 in the 4s and 5 in the 3d. That's the maximum that you have. So that's kind of giving you the range. +2 उन सबने करनी है and maximum उन सबको empty कर सकता है. Copper के case में +1 भी करता है. Iron onwards, +2 is most common. Why? Because of effective nuclear charge. That makes it really, really difficult to remove them. And another important point to remember here is that just because they can afford to lose all electrons does not mean that they will always do. They have to be joined with a really strong electronegative substance to make that. So chromium +6 बना सकता है ना, लेकिन वो खुशी से नहीं बनाता हर जगह पे. When it is bonded with something like oxygen or fluorine, that is when it does that. So higher electronegative ions or elements are required to achieve highest oxidation states. So some example of this would be chromium +6, which is over here, or manganese with the manganate ion that we have, MnO4. In this one, manganese is 7. Okay, this is +7 and this is +6. Or it's all because ऑक्सीजन के साथ ज्वाइन हुआ हुआ है. फ्लोरीन के साथ भी जब वो बॉन्डिंग करते हैं तो वो इसी तरह से बनाते हैं. A couple of questions that you need to be able to answer, like why does what's the configuration of copper +1 or configuration of nickel +2? ये आपको आनी चाहिए. Why is scandium and zinc not considered transition metal? Why does manganese go up to +7 only? उससे ऊपर क्यों नहीं जाता है? Okay. Similarly, they can ask you about different colors that you will need to remember. I will share the color chart with you in the WhatsApp group. तो वो आपको वहां से मिल जाएगा. Then they use the same ideas and they extend it to bigger periods. Like, for example, yeah, let's take zirconium. So zirconium, its key configuration is kryptons configuration, and then 5s2, 4d2. So based on this, or let's say you write this, by the way, आप ऐसे लिख दो या ऐसे लिख दो, they're both acceptable. So tell me, what is the most common oxidation state this will have?
2+.
2+. Zirconium exists as +2. What is the maximum oxidation state zirconium will show? Which is stable. मतलब unstable तो हम कोई भी करवा सकते हैं उससे. Maximum stable configuration. Yeah, oxidation state.
Is it +4?
It is +4. Very good. So if I asked you, there are two kinds of oxides that zirconium makes. What will their formulas be? It will be ZrO and ZrO2, because oxide is -2. So -2, you can bond it with this ZrO, or you can have ZrO2. Yeah, so that is something that examiner can sometimes test. कि अच्छा आपको concept आता है कि वो कैसे बनती है उनकी oxidation state. So you can usually just extend it to other ones. Now, if you look at the physical properties of these things, so we have a whole range of physical properties which we know from grade 9. We know that they have high melting point, they have high density, they are strong, and you can make alloys which will be really, really rigid, or they can withstand a lot of weight, so they're really strong. They are excellent conductors of electricity, of heat. They have variable oxidation states, as we have seen. Because of these variable oxidation states, they show colors, which we'll talk about. कि वो colors कहाँ से आते हैं. And There's another one because of this that they form complexes. That's something new for us in A2. We will talk about that as well. And then that they can be used as catalysts. Okay, again, because of this variable oxidation states, and we'll do examples of that, how they're able to do this. And this whole process is obviously redox reaction, that they're able to lose or gain electrons of variable number of electrons that they can do. But then there are some trends that we see here. For example, why do they have higher melting point than S block in the same row or P block in the same row? Why is that? Or metals that are very close to these, D block walon ke melting point zyada kyun hota hai? And that is because every time you have melting point, you have to talk about the forces of attraction that are being broken. In the case of metals, they have metallic bonding. So the force of attraction is between cations and the sea of electron. Now, transition metals can give electrons from 4s and also 3d. For example, copper 3d mein se electron deta hai for the metallic bonding. Now, that gives them a much that gives them an edge क्योंकि उनके पास electrons ज़्यादा हैं donate करने के लिए for the electron cloud या sea of electron. So because they have more electrons to donate to that, they have a much stronger force of attraction compared to, let's say, calcium. It's in the same row. It also has 4s2, but calcium अपने 3p से electron दे नहीं पाता. They can give electrons from 3d. So because of electrons from 3d and 4s being involved in metallic bonding, they are better conductors. They are high melting point, stronger, वो सारा कुछ उनका वहीं से आ जाता है because they have stronger metallic bond. Okay, and they're better conductors. They are more what you call, they have higher melting point. All of that is fine, but what about density? Again, from left to right, ionic size decreases, right? Because effective nuclear charge is higher. So their ions are smaller than ions of, let's say, calcium in the metallic lattice. So ion छोटा है, charges ज़्यादा हो रहे हैं, और electrons भी बहुत ज़्यादा हैं. So the force of attraction is also really high. And this makes that they have higher density. So one question could be, why do they have higher density than calcium? So that will be that they have smaller radii and higher masses, because left to right mass to बढ़ रहा है, तो इसकी वजह से higher density compared to calcium, for example. Similarly, there can be a question कि अच्छा ठीक है, मान लिया कि smaller radii, but here's the thing. Here's a very weird question that took a long while to answer. Why is it that within the same what you call the row, the radius doesn't drop as it usually drops in other periods? So for example, अगर मैं आपसे कहूँ ना कि सोडियम, मैग्नीशियम, एल्यूमिनियम, उनके पीरियोडिक, उनके रेडियस को आप देखो तो उनका रेडियस ना इस तरह से फॉल करता है. On the left side, you have sodium, which has a very high radius, big radius. And on the right side, you have chlorine, which is a low radius. But in the case of transition metals, it's more like a straight line like this. From left to right, like scandium se leke copper tak ya usse aage. Scandium ko chale nikal dein because it's not a transition metal. Titanium se leke copper tak, their radius is roughly the same. बहुत ज़्यादा difference नहीं है. Why? You are adding more electrons. There should be more shielding. You should be getting more electron pair repulsion. But that electron pair repulsion is coming from the same 3D now, not from 4s. 4s तो इन सबका completely filled है. So they have electrons coming over here. So जो भी shielding आनी है, वो इसी से आएगी, not from the last shell. So बहुत ज़्यादा size increase नहीं करेगा. And at the same time, you're adding more protons, which are adding more strength to the atom, the effective nuclear charge. So effective nuclear charge, even though it increases, and electron pair repulsion also increases. This should reduce the size of the atom. This should increase the size of the atom, but the effects are cancelled out. So their effects are counterbalanced or cancelled out. So radii are roughly the same throughout. And that's interesting because they all behave like similar kinds of radius ions in a very strong lattice. And at the same time, this is also the reason why their last shell 4s is the one where you're removing electron from. So uski wajah se kya hota hai? That, wait a minute, you should talk about the d orbital electron pair repulsion and mention that last shell is still 4s. So 4s2 is the last one. So when you're removing electrons, ionization energies should also be the same. Why roughly the same? Because the last electron that you have to remove is from 4s2. So अगर उसको आपने remove करते हुए आपको energy तकरीबन एक बराबर लगेगी because उनके sizes भी एक बराबर है, और आपको नए electrons add करते हुए भी आप size को increase नहीं इतना ज़्यादा करें क्योंकि वो तो वहीं पे है last shell. आप तो last shell में कुछ add कर ही नहीं रहे, आप तो inner shells में electrons add कर रहे हो. And that is why the whole idea of 4s versus 3d, that is the crux of today's lesson. Okay, how 4s being the last shell affects the properties of these when electrons are being added to 3d. This is the first case in which we are seeing this. We have not seen this in any other element in the periodic table. Calcium को अगर आप ले लो, उसमें ऐसा नहीं होता. Potassium और calcium में जब आप electron add करते हो, it's always added to the last shell. In the case of transition metal, you already have the last shell filled. You're adding electron to the inner shells. And you're removing electron from the outer shell at the same time. So ionization energy change नहीं हो रही, लेकिन atomic size भी change नहीं हो रहा है. So all the effects that we are used to seeing since AS, कि अच्छा electron add होगा तो effective nuclear charge पे effect आएगा, ionization energy पे effect आएगा, atomic radius पे effect आएगा, वो सारा कुछ जो है यहाँ पे नहीं चल रहा है. So I will share some notes with you for 4s versus 3d and how that affects the whole behavior of transition metal, and kind of like that whole thing defines the behavior of transition metal in many, many aspects. So that is where I would like to end the lesson today. The idea of 4s versus 3d. I will share the notes with you, go through it, think about how the configurations are, how it affects the ions that they make, and how it affects the physical properties that they have. Okay, we'll talk about orbitals and the arrangement and the impact of that more tomorrow.
Thank you, Sir Al-Hafiz.
Okay,
Hafiz.